Alright, I want to start this video by going over the second mystery of the 1900s. So the second mystery is called the photoelectric effect, and of course this was solved by Einstein in 1905. On the right, we have an apparatus which was used to study the photoelectric effect. The apparatus shows light of a certain frequency falling on a metal surface. Electrons, when that light hits that metal surface, electrons are ejected from the metal. And when those electrons are ejected, they're attracted towards the positive electrode. The flow of electrons is basically registered by the meter down here. Depending on the intensity of the light, you will get the meter to go higher, right? So it's registering a flow of electrons. That effect couldn't be explained by the wave theory, but it can be explained by the particle wave duality theory, which that's what Einstein proposed. Because think about it, if it's a wave, how can you measure an intensity if the wave is supposed to be continuous? So the fact that they can measure something with this meter means that light is not only a wave. Light must be composed of other things. So what Einstein proposed is that light has both a wave nature and a particle nature. So therefore the particle wave duality theory. Einstein basically made that assumption, and he said that the beam of light is a stream of particles called photons. Of course, using Planck's quantum theory, he deduced that each photon must possess h nu of energy, that quanta of energy that we talked about in the first video. So again, electrons are ejected from the surface of certain metals that are exposed to light. The number of ejected electrons is proportional to the intensity, the brightness, of light. But below a threshold frequency, no electrons were ejected no matter how intense. So that's another part of this mystery, is that they were proportional depending on the intensity of the light, but sometimes doesn't matter how bright the light is, if it was below a certain frequency, no electrons were ejected. And this was explained by Einstein because electrons are held in a metal by attractive forces. So to remove them, you need sufficient energy to break them free. If you shine light, basically a beam of photons, that's exactly equal to the binding energy of those electrons to the metal, then the light will have enough energy to knock off the electrons. But if we use light of higher frequency, then not only will the electrons be knocked off, but they will also gain some kinetic energy. That situation is basically summarized by that equation. H nu is equal to kinetic energy plus the work function, where Ke is the kinetic energy of the ejected electron and W is the work function, which basically is a measure of how strongly the electrons are held in the metal. We can of course rewrite the equation to solve for kinetic energy, which shows that the more energetic the photon, aka the higher the frequency, the greater the kinetic energy of the ejected electron. So basically what we learned here is that light has a particle wave duality. It acts as a wave sometimes and it acts as a particle sometimes. We learned about the photoelectric effect, and we learned that light has to be of a certain frequency to be able to eject electrons from that metal. And depending on how intense that light is, you will get a stream of electrons registering at a meter. Let's consider this. If two beams of light having the same frequency, which is greater than the threshold frequency, so you're definitely registering a flow there. So consider two beams of light having the same frequency, but they have different intensities. So the more intense beam of light consists of a larger number of photons registering in the meter, because consequently it ejects more electrons than the weaker beam of light. So basically the more intense the light, the greater number of electrons emitted. The higher the frequency of light, the greater the kinetic energy of the ejected electrons. Alright, let's do a problem. Alright, let's do these two problems. The energy of a photon is 5.87 times 10 to the negative 20th joules. What is the wavelength in nanometers? So for this problem, I am going to use E equals h nu. The problem is that they give me a wave, they want to know the wavelength. And in that equation, I don't have a wavelength, but I do know that I can substitute another equation. Remember C equals lambda nu? Well, I can go ahead and solve for nu, which would give me nu is equal to c over lambda, and I can plug that back into the original equation that I'm using. So I would end up having E equals Planck's constant times speed of light divided by the wavelength. Now all I got to do is solve for wavelength. So it would be wavelength is equal to h, speed of light, over energy. Now it's easy. All I got to do is plug everybody in. So 6.63 times 10 to the negative 34th times the speed of light divided by 5.87 times 10 to the negative 20th gives me the answer in meters. So I have to convert to nanometers, which gives me 3.39 times 10 to the third nanometers. Really simple problem. The hardest part here is that you have to remember that you can combine those two equations, the E equals h nu and C equals lambda nu, to get any combination of those variables. All right, let's do the next one. The work function, all right, so this problem is going to deal with the equation that we just learned after the photoelectric effect. All right, so the work function of cesium metal is 3.42 times 10 to the negative 19th joules. Part A. Calculate the minimum frequency of light required to release electrons from the metal. All right, so I know which equation I need to use. I need to use h nu is equal to kinetic energy plus work function. All right, they're asking me what is the minimum frequency of light that's required to release electrons. I know the work function, I know Planck's constant, so the only thing I really have to figure out is what do I put for kinetic energy. Well, it tells me the minimum frequency of light required to release electrons. So no extra kinetic energy here. I just want enough energy to bump off those electrons. No extra kinetic energy, so that means I can put a 0 at where kinetic energy is. So I end up having something like nu is equal to kinetic energy plus work function divided by Planck's constant. But I'm going to put a 0 where the kinetic energy is. Then I have the work function, 3.42 times 10 to the negative 19th, divided by Planck's constant. That gives me a frequency of 5.16 times 10 to the 14th hertz, or 1 over seconds. All right, part B. Calculate the kinetic energy of the ejected electron if light of frequency is now 1.00 times 10 to the 15th hertz. So in this case, I'm going to solve for kinetic energy, use the same equation, but solve for kinetic energy, which is kinetic energy is equal to h nu minus the work function. And all I do here is plug everybody in. I know Planck's constant, I know what the frequency is because they gave it to me, minus the work function, which of course is the same, 3.42 times 10 to the negative 19th. If I multiply all that together, I end up having a 3.21 times 10 to the negative 19th joules. So that's what kinetic energy that electron has when you applied a frequency of light that happens to be 1.00 times 10 to the 15th hertz. All right, let's move on. All right, this is section 7.5. We are not going to go over section 7.4 or 7.3, so we're skipping over to quantum mechanics. Another discovery that was really important back in the 1900s was that electrons also have a dual nature. So they also act like waves and particles, depending on what situation they're in. But with that discovery comes a huge problem. If electrons are indeed wave-like, how can the position of a wave be specified? So for example, how can we know the position of an electron if we can't define the precise location of a wave because a wave extends into space? This was a big problem. So if we wanted to locate a subatomic particle, that would be pretty difficult. To describe the problem of trying to locate a subatomic particle that behaves like a wave, Werner Heisenberg, did any of you watch Breaking Bad? But anyway, Werner Heisenberg formulated what is now known as the Heisenberg uncertainty principle. And basically what it states is that it's impossible to know both the momentum, which is mass times velocity, and the position of a particle with any type of real certainty. That sign that you see greater than or equal to means that the product of the position and the momentum can be greater than or equal to h over 4 pi. But it can never be smaller than h over 4 pi. So basically this equation states exactly what I just read, but mathematically. It's impossible to know both the momentum and the position of a particle with any real type of certainty. Delta x and delta p are the uncertainties in measuring the position and the momentum of the particle. The significance of this equation is that in even the most favorable conditions for measuring position and momentum, the product of the uncertainties can never be less than h over 4 pi. So what that means is that if the measurement of the momentum of a particle is becoming more precise, then correspondingly the position must become less precise, and vice versa. Applying this principle, this Heisenberg uncertainty principle, to, let's say, a hydrogen atom, we saw that in reality the electron does not orbit the nucleus like in a well-defined path, as earlier scientists thought. If it did, we could determine precisely both the position of the electron and its momentum. All right, let's try a problem with this. All right, this is problem 128 in the back of your chapter. It says, alveoli are the tiny sacs of air in the lungs whose average diameter is 5.0 times 10 to the negative 5 meters. Consider an oxygen molecule, which has that much mass, 5.3 times 10 to the negative 26 kilograms, that's trapped within a sac. Calculate the uncertainty in the velocity of the oxygen molecule. And they give you a hint. The max uncertainty in the position is given by the diameter of the sac. Since they want to know the uncertainty in the velocity of the oxygen molecule, I'm going to go ahead and use the equation that we just learned. It's delta x times delta p is greater than or equal to h over 4 pi. Since they want to know the velocity, I'm going to go ahead and solve for p, momentum, because remember, momentum is made up of mass times velocity. So first I'm going to input that, so it's going to be delta x times mass times velocity. And I'm going to go ahead and just change the greater than or equal to sign to just an equal to sign. Equal to h over 4 pi. Now I'm going to solve for velocity, which leaves me with v is equal to h over 4 pi times mass times the change in position. Now all I do is just plug everybody in. So 6.63 times 10 to the negative 34th joules seconds divided by 4 pi times 5.3 times 10 to the negative 26 kilograms times 5.0 times 10 to the negative 5 meters. If I multiply all that out, I get 2.0 times 10 to the negative 5 meters per second. The units that you end up with is joules seconds over kilograms times meter. But they want the velocity, and velocity is in meters per second. So I know that a joule, because I went back to page 202 in your book, a joule is equal to kilogram meter squared over second squared. So if I put all that together, what I have in this equation and what I know a joule is, it ends up being kilogram times meter squared times second divided by second squared times kilogram times meter. And you can see that the kilograms cancel out, one of the seconds cancel out, and one of the meters cancel out. So you end up with meters per second. The final answer again is 2.0 times 10 to the negative 5 meters per second. That is the uncertainty in the velocity of the oxygen molecule that's trapped within an alveoli sac.